Hi, everybody, and welcome to VSAONLINE again. Before I introduce our guest today, I would like to remind you about last days for applying to or for signing up for our physical meeting here in Luleå. So if you consider spending some time in northern Sweden, so please take this opportunity. So 15th and 16th of June, so in 1 month from now. So we have a physical workshop here in Luleå. So I will send a separate email with a reminder for registration. So we have a couple of vacant places left. But apart from that, so I'm very happy to introduce Dehao Yuan from University of Maryland. And without any further delay, I give the floor to him.
Okay, so good morning, good afternoon, good evening to everyone. It's my great pleasure to have my presentation here about my new RIP submission, decodable sample invariant continuous object encoder. So there are several keywords here. The first is decodable and sample invariant and continuous object. So please allow me to first introduce what is continuous objects, and then we will see what can we do out of that. So what is a continuous object? A continuous objects are objects that can be sampled with arbitrary resolution or distribution. So for example, here we give 3 examples of continuous object, like a surface, a level set, or a vector field. For a surface, you can think of it as a mapping. So in this case, it's a mapping from R2 to R. So it's a 2-dimensional function. And for level set, it is an intersection of a plane with a surface. So like the red curves here would illustrate the level set. And third, a vector field can be viewed as a function from R3 to R, because for each coordinate, it has a pointer, it has a vector pointing to the direction of the flow. So what's the commonality of those 3 objects? The commonality is they can be sampled with arbitrary resolution or distribution. For example, in a surface, here the grid illustrates one way of sampling the surface. However, of course, the grid can be sparser or denser. So you can see a surface can be sampled with arbitrary resolution, and similarly for others. So that's like a theoretical concept of continuous object. But in practice, is there any example? And the answer is yes. So in practice, we can also see many data which will be presented in a form of continuous object. Like for the event camera, event frames captured by the event camera, those events are like the 3D coordinates in the time and pixel coordinates. So those are very sparse sample. And for meteorological measurements, for example, if you have satellites taking image on the Earth and measure some meteorological variables, then you can see the measurement is actually sparse measurements. And similarly for point cloud, it's also like a data collected from some continuous surface. So in practice, the sample distribution and resolution. So in all these 3 examples, the sample distribution or resolution can vary between the training phase and the testing phase. For example, in your event camera, during the testing, your event may be sparser or denser than your data in the testing set. So here is a very important and significant feature of continuous object. So our question would be, is it possible to have an encoder, a continuous object encoder, that can receive the continuous object and then construct a vector representation of the continuous object? And of course, the representation of the continuous object is their samples. For example, here you can collect samples of a surface and then pass the samples to this continuous object encoder, and then produce a vector representation. So this is our research question. Can we design a continuous object encoder? And of course, we should have some desired property of this continuous object encoder. First, the first two properties are very important because just I have mentioned, for a continuous object, you can sample it with arbitrary sample distribution or sample density. So here in this figure on the left-hand side, you can see here is the curve is a continuous object, and you can sample the curve with arbitrary sample distribution. So here, if you zoom it in, there are some blue samples. It is denser on the left-hand side, and there are some green samples, which is denser on the right-hand side. Based on these two different samples, we can construct vector representation of this continuous object. So we want to encode the curve into the vector representation. But from two different samples, it may construct two different vectors, but we require that the two vectors should be invariant to each other, because whatever sample it is, it actually represents the same continuous object. So it is very natural to have a property saying that the encoding is invariant to the sample distribution and sample density. So that's the first two properties we desired. The third property is a decodable property. It means that given the vector representation, you can decode the vector and reconstruct the original continuous object. So here, for this part, it demonstrates the decodability property. So the final property is we hope we can have an explicit representation. So in this case, it is a vector representation. So we desire these four properties. Why is that? Because with these four properties, we can have applications of this framework. There are two major applications. The first is you can receive a continuous object as input and encode it into a vector representation, and then pass the vector to a neural network. And then you can perform some machine learning task like classification or regression out of this continuous object. Another application would be you can predict a continuous object. For example, here you can have any input, and then you pass the input to a neural network, produce the embedding of the continuous object. And because the vector representation is decodable, you can decode the vector representation back to the continuous object. So that's the motivation of these four properties, because we want to have two applications. The first is you want to receive a continuous object as input. The second is you want to predict a continuous object. So that's the motivation of our problem.
So Dehao, just one question to your desired properties. So how can this be that that it's independent, that it's invariant to sample distribution? I mean, if you don't know any data points on the left side of the curve, how can you know what the curve is? So I just don't understand this. If you have some fixed sample, how can you form a representation which is invariant of the sample distribution?
Yeah, thank you for a question. It's a very good question. And actually, I would have a very detailed discussion in the later of my presentation. So later, I will present my method, which I claim that it would satisfy the two properties, regardless of the sample distribution and sample density. So we have a theorem proving that we have this property. And later, I will have a much detailed discussion on that. But here it's like a motivation to say that these two properties are important.
Sounds a little bit magic, but go on.
Yeah, thank you. And with the problem definition, then I would like to have a introduction of our work. So first, we will introduce some existing frameworks which try to solve the continuous object problem. And then you will see that the existing framework will be divided into three categories. After introducing the frameworks, we will introduce our own frameworks. We'll name it as HDFE, so hyperdimensional function encoding. So we will introduce our own framework, and then we will demonstrate two interesting applications of our framework. And finally, we'll have the conclusion and future work. So let's look at some existing frameworks. So one type of framework is discrete frameworks. So in these frameworks, they usually discretize the continuous objects and process them with convolutional network or recurrent network. For example, on the left-hand side here, like in the event camera event frames processing, we will usually have those like sparse event data, and then some of the paper will voxelize the event and make a 3D image like this. And of course, some other paper would try to convert the event frames into RGB image like this or that. So that's one approach to to deal with this continuous object. Basically, they discretize the continuous object. And similarly for the right-hand side, so it would use the recurrent network to predict the object, the particle trajectory. So here, for example, they will first discretize the continuous 2D space, and then for it, so it would be it would discretize the space, and then it can predict the probability of the article, like you travel to which discretized region. So it's another example of a discretized framework. So what's the disadvantage of these frameworks? The disadvantage is that it is not sample invariant. Why is that? Because when you have your testing data like collected in a different sample distribution or different sample density, then the voxelize, then you have to match the temporal or spatial resolution between your training time and testing time. So this discretized framework is not sample invariant. And another type of framework is a mesh grid-based framework. So they usually operate on mappings defined on a mesh grid. So for example, here there's a figure from neural operators. They consider the mapping between the initial velocity to like what's happening during arbitrary time. So basically, they would consider predicting. So they will have a neural operator predict what happens from between initial to arbitrary time. So this kind of methods, they would model the mapping between function spaces, and those functions are defined on a mesh grid. So like here, the function is defined on a two-dimensional grid, and the output solution is also represented in a two-dimensional grids. So this kind of methods, they can achieve discretization invariance. So what does it mean by discretization invariance? It means that whatever the resolution of the function, it actually the behavior of the frameworks is totally the same. So there's discretization invariance. But what is the disadvantage of this method? It lacks an explicit representation of the function. So in those neural operators paper, they only consider like mapping between function space. Like for example, you can map the initial velocity to like the state in arbitrary time. However, it does not provide an explicit representation of like this or that. So that's one limitation. The other limitation is it is not scalable, because if your function has to be defined on a mesh grid, then in a high dimensional case, it can be very hard because your mesh grid will grow exponentially. So it is not scalable to a high dimensional data. And the third types of frameworks is sparse frameworks. They would operate on the sparse samples drawn from the continuous object. So for example, if you have a two-dimensional sphere, then you can collect sparse samples from this sphere. And then the sparse framework can operate on these sparse frameworks. It is not necessary that you are sampled on a mesh grid like this. So one representative of this framework is the point net, which is a very famous architecture. So the point net will receive the sparse input, and then by some multi-layer perceptron, it would produce a local feature of all the points. And then by a max pooling operation, it will produce a global feature. And then the global feature will represent the whole input points. And then by connecting with some neural network, you can perform like classification or segmentation. So that's the architecture of PointNet. It can receive sparse input and produce a global feature. However, the disadvantage is that it is not decodable. What does it mean? It means that given the global feature, you cannot actually reconstruct the original distribution of the points. So that's limitation of PointNet. So in a sparse framework, there is another framework called vector function architecture, in short VFA. So it also operates on sparse sample from explicit functions and then produce an explicit encoding. So actually, this is a previous. Actually, our paper extends is inspired by this paper, and then we make some extension on that. So what vector function architecture do is, so they consider a function which can be written as a linear combination of a kernel, and then the function can be represented as a weighted average of the embedding of the samples. So here in this architecture, it can actually achieve the sample invariance and decodable. So it is decodable. And in this paper, we extend the VFA by having some like amendment to it. First, we enable implicit function encodings, because you can see in the VFA architecture, in order to encode a function, you need to write it as an explicit form, y equals to fx. But in our paper, we can enable implicit function encoding. Second, we also apply the framework to some real-world applications. So it's like a demonstrate. It's demonstrate there is a wide applications of this kind of framework, and hence you can like have many future directions. So that's the motivation of our paper. So after introducing the existing framework, we will introduce our own framework. So in this paper, we propose hyperdimensional function encoding, which in short, HDFE. So in the following section, we will introduce it in the following way. First, we will introduce how to use HDFE to encode in explicit function. And this can be separated into three parts. First, how to encode a function. Second, how to decode the original function from the encoding. And third is how we can ensure a sample invariance of our like HDFE. After introducing the explicit function encoding, we will generalize the methods to implicit function encoding, and then we will see what can and then we will see how the framework can be applied to real-world application. So for a vector valued function, we will choose some appropriate like tricks to realize the frameworks. And finally, we will discuss the properties of HDFE. So first, let's look at the explicit function encoding. So let xi, yi be the samples of the function. Then the vector representation of the function is produced by super precision of this is a row filler binding. So basically, suppose you have the input x, and then it maps to output space y, and then what HDFE do is it uses an EX, which will map the input space to a high dimensional space. So this is a high dimensional space. And also similarly for EY, it also maps to a high dimensional space, Cn. And then by binding this, by binding the two vectors together, it will produce a joint distribution. It will produce a joint embedding. So this is basically EX bind with EY. So here, for each of the sample, it will produce a joint embedding in a high dimensional space. And then by superpositioning them, then this will produce a collective representation of the function. So suppose the data is representative enough, then this superposition can capture the distribution of the function. So here we have several requirements. Remember, we have EX and EY. And for EX, it has to satisfy the following property. So what does it mean? It means that, so consider here, there's a black point here. Suppose in the function space, like the blue points are very close to the black points. Then in the hyperdimensional space, they are close to each other. But once the distance between the green point and the black points, when the distance goes larger, then the similarity would decay very quickly. So here, for example, the black point and the green point, they are a little bit far from each other. But in the hyperdimensional space, they have been very far away. And for the green point and those blue points, so it becomes much more far away and almost orthogonal to each other. This is the requirement of the EX. So, and for the requirement of EY, it is not that strict. It only requires, oh, sorry, there's a typo here. So this is EY Y1 and EY Y2. The cosine similarity should be greater than 0 for all Y1, Y2. And you will see that this is because we want to have a better reconstruction accuracy later on. So after the encoding, we can discuss the decoding. So given the vector representation VF and the query point X0, then the estimated function value is by a similarity search. So recall that the VF is a summation of EX bind with EY. So suppose you unbind with EX X0, then of course you will get approximately EY Y0. This is so if you search for the Y which maximize the cosine similarity, it can produce the estimated value of Y0. This is the decoding. And because we require the EY, so we require EY Y1 and EY Y2 to be greater than 0 for all Y1, Y2. So this searching can be done using some searching algorithm like Nelson meld. This is what we used in our paper. So why does that happen? It is by a very standard HDC argument. So when you unbind with EX X0, then when X0 and Xi is close to each other, they will be approximately equals to EY FXI. But when they are far from each other, then it will produce some random noise. So it's a very standard HDC argument. So that's why this encoding works. And then we will discuss how can we ensure distribution invariance. So this is a very important part of our paper. So imagine if you only do the simple average of the samples, it is density invariant because here we normalize it. So whatever sample, how many sample you have, the vector will always have the norm equals to 1. So it is density invariant. However, it is not distribution invariant because suppose your sample is very dense in here, but very sparse, like here. Suppose your sample is dense here, but sparse here. Then this summation would be close to the dense part, but it would forget the sparse part of the data. So in order to avoid this thing, we have an iterative refinement process. So here, let Zi be all the encoding of the samples. And then here we compute the simple average. So at this stage, it is nothing new. But here we compute the minimum cosine similarity between VF and Zi. So we choose the sample that is farthest away from the average and then add the sample to the vector representation. So you can imagine if the if your sample is here, if your average is here, so this is your VF, and then suppose there is a sample very far away here, so this is CJ, so this is CJ. Then if it is far from each other, if you add CJ to VF, then the VF will get closer to ZJ. So this is VF prime. So after this iterative refinement, it will finally converge to a state that the minimum cosine similarity does not increase. And this will be the final function representation. And why does that iterative refinement will work? It is because actually, if you look at this iterative refinement, it is actually solving a complex, it is solving an optimization problem. It is maximize the minimum cosine similarity between the VF and the ZJ. So the solution is actually the center of the circle covering the all the points. So here, suppose the sample points are the red circles, and then the blue circle here covers all the sample points, and then the center of the circle would be our final VF. So as you can imagine, this center of the circle does not depend on the distribution of this sample point. It only depends on the supports of the sample point of the distribution. So that's how we can achieve distribution invariant regardless of the sample distribution. And then after introducing the explicit function encoding, we can introduce how to generalize the explicit function to implicit function encoding. So this is actually very straightforward. Let xi be the samples on the explicit function fx equals to 0. Then the function encoding is very simple. It's simply constructed by summation of all the embedding of the samples and followed by the iterative refinement. So this can be understood in the following way. So the implicit function can be written in this way. Let gx equals to 1 if fx equals to 0. It means that if x is on the implicit function, then if gx equals to 1. If fx is not on the implicit function, then it equals to 0. And then we can let vf equals to 0, which is the implicit function, is equals to vg. And then it actually equals to the summation of exx, because remember we are sum over exx bind with eyy. So suppose we let ey equals to 1 and ey1 equals to 1 and ey0 equals to 0, then it would produce this formula. So that's how we can generalize explicit function to implicit function. And finally, we will discuss how can we choose the ex ey, because here I haven't thought about any realization of this ex and ey. The question we ask is what ex ey and the binding operation should we choose to realize this framework? And the answer is we use the fractional power encoding, which has been quite popular in the HDC community. So basically what fractional power encoding do is exx is equals to, first you multiply x with a matrix to lift the input to a high dimensional space. So here it would do from x and then map to a high dimensional space Cn. So this is how you do. And then by an exponential exponential and then multiply with the imaginary unit, it would distribute the points into a unit circle in a complex domain. So like this. And then by taking an inverse Fourier transform, it will produce some random points in the complex domain. So this will be the final representation of the sample. And similarly for y, it is basically using the same formula. And the binding operation is the binding operation is the circular convolution between the two vectors, which can be written as the Fourier transform and then multiply two things together. So Fourier transform and then you multiply these two together. So that's a circular convolution. And for binding, it is a circular correlation. So here you are not multiplying, but dividing the two things. So here alpha and beta, so you can see alpha and beta are two tunable parameters, and we will discuss what is the property of alpha and beta. So here recall that we require so for the input space Ex and Ey, we need the cosine similarity of two inputs to be approximately equals to 1 if the distance is small, and approximately equals to 0 if the distance is large. And by looking at the figure on the left-hand side, you can see we can choose appropriate alpha. So here, for example, alpha equals to 0, then the cosine similarity behaves in this way. If alpha equals to 3, then the cosine similarity behaves in this way. So we can choose alpha to control the epsilon here. So that's why we apply the fractional power encoding. So this is in one-dimensional case. In two-dimensional case, it is also very similar. This for the middle figure, it is alpha equals to 10. For the figure on the right-hand side, it is alpha equals to 30. So as you can see, the epsilon can indeed controlled by the alpha value in this formulation. And for Ey, so for Ey, remember we require Ey_y1, Ey_y2, the cosine similarity to be greater than 0 for all y1, y2. So this can also be controlled by choosing appropriate beta. So if you remember that here is a totally same formulation. So by choosing beta, so here if you choose beta equals to 1, then the cosine similarity will be greater than 0 for all y1, y2. So that's why we choose the fractional power encoding to realize our Ex and Ey. And then we see what happens when we tuned the alpha and beta. So here suppose you use a small alpha. Small alpha means that so like the similarity would decay to 0 very slowly. When you use a small alpha, you would tend to forget the high frequency details in this in the function. However, when you increase the alpha but do not increase the dimension of the function, it tends to it tends to reconstruct the function with inaccurate result. However, this can be resolved when you use a higher embedding dimension. So when you use a big alpha, you can see you can capture the high frequency details of the function, but do not incur any reconstruction loss. So that's the effect of the alpha and beta in our framework. And here we discuss several properties of HDFE. The first property is very important. It is sample density and distribution invariance. So it means that suppose your Xi is drawn from some distribution, and then the sample are fed to HDFE, then the resulting representation is invariant of the sample density and sample distribution of P. So actually in the paper, we have a detailed proof, but I think a very intuitive sense, I have mentioned that before, it is the final representation is the center of the circle covering all the sample points. So that's the intuition behind. Second property is it is a distance preserving mapping. So suppose you have F and G, they are both mapping from X to Y, then their L1 distance is preserved in the encoding. It means that if you compute their L1 distance, then the L1 distance is proportional to the negative cosine similarity between the function representation. So in the paper, we also have a detailed proof. So if you're interested in that, you can look at our paper. And finally, we have a conjecture that our HDFE can scale to high dimensional data. It is because the required dimensionality does not depend on the explicit dimension of the data. For example, suppose you have from R64 to R, then it does not mean that we need to have such a high dimensional to accommodate the 64 dimension. So suppose the data is resides on in a low rank subspace, then the dimensionality we need is much less. So that's a conjecture. So we conjecture that this can scale to high dimensional data. It does not depend on the explicit dimension, but only depends on the inherent dimension of the data. So finally, we have two interesting applications of HDFE. So first problem is a PDE solver. So we want to map PDE to its solution. So remember, PDE is a function and its solution is also a function. So here is x prime. So suppose this is x prime equals to fx and the solution is xt. So the input is a function, the output is also a function. So we can map the PDE to its solution. So the architecture will be you first encode the PDE into a vector representation and then use a very simple neural network to predict the encoding of the solution. And then you can reconstruct the original function from this encoding. So here we use two benchmarks. The first is a Berger's equation. The second is a Darcy flow. So Berger equation is a 1 dimension and Darcy flow is 2 dimension. The data set is provided by a previous paper. And here is the experiment result. So here we compare 3 different baseline, PCAN, MGKN, and Fourier neural operator, FNO. So as you can see, our error, it is shown here. It is about 55% lower than the previous 2 baseline. And it is slightly higher than the Fourier neural operator. But this is because we have a reconstruction error incurred, because we need to, after predict our embedding, we need to reconstruct the original function, and here it incurs some loss. Here it incurs some reconstruction loss, and the reconstruction loss is visualized here in a transparent red bar. But for Fourier neural operators, they directly mapped the function to function, so it does not have any reconstruction loss. So it would be slightly, there would be a slightly lower error. However, if you only consider the function prediction loss, so suppose we only consider the function prediction loss, then our error is much lower than Fourier neural operator. And actually, we demonstrate that the reconstruction error can be improved by enlarging the dimension of the vector. So here we increase the dimension of the vector, and you can see the reconstruction loss can decrease. Even though the function prediction error may increase a little bit, we think it may be due to a limited training data. So we conjecture that this can be improved when using a higher, using a larger data set. So that's 2 key messages we want to convey. So with reconstruction, we can achieve on par performance as Fourier neural operator. Without reconstruction, we can achieve lower error than Fourier neural operators. And similarly here for the Darcy flow, this is the evaluation on the Darcy flow. And here we show some qualitative results. The left-hand side is an input function, and in the middle, it is the ground truth solution. And on the right-hand side is our prediction. As you can see, it is very accurate. And then we have the second application is the local geometry prediction problem. So what's the problem? The problem is, suppose you have a service, and then you will collect some samples of the service, and then the problem will predict the normal of this service at this point. So the benchmark dataset is the PCPNet. The architecture is actually very simple. Suppose you have a collection of your points, and then by our HDFE, you can represent it as a vector. And then by using a neural network, very normal neural network, you can predict the surface normal, and then you minimize the cosine similarity. And here is the experiment result. Here are two different settings. The first is noise. So basically we will add Gaussian noise to the point coordinates. So the magnitude will be divided into low, mid, and high. So in this setting, you can see that when the noise is mid-level or high level, our model would achieve a much lower error than the state of the art, actually about 22% lower error. So it is very robust to the noise, to the point perturbations. On the other hand, in the density variation, it means that the density of the points, the sample distribution may vary between the training set and testing set. In this setting, we can see that our method does not incur any error increased, but for others, they all incur some levels of error increase. So under this setting, we can see that our method is very robust to density variation. So that's the two major message takeaway. And to summarize, we propose a continuous object encoder, which is sample invariant, decodable, and isometric, which is distance preserving. And we have some theoretical foundation for HDFE by proving the properties, by proving the three properties. And we also have empirical experiments to verifying them. And finally, we demonstrate HDFE can be applied on some mesh grid data or sparse data. So mesh grid data is talking about the PDE solver. The sparse data is talking about the geometric prediction. So HDFE exhibits a very strong robustness to noise and sample variance. That's the major takeaway of this paper. And finally is the future work. As you can see, we have two applications of HDFE, but you can imagine we can have many other applications. For example, we can use it to process the event frames captured by the event cameras. Because of the sample invariance property, the discrepancy between training set and testing set can be very well addressed using our framework. And also point cloud data is similarly. And third is resolution independent image processing, like super resolution or image to image translation, this kind of applications. And finally, we can also deal with data with mixing pixel. So it's like a sparse data scenario. And this is the 4 applications that I can think of. And we can also further develop the HDFE. First, we may want to automatically search for the appropriate kernels. So here, remember, EXX is equals to Fourier exponential I alpha phi x divided by n. So here we want to search for appropriate phi here, so that the reconstruction can be good. And finally, we can think about how the HDFE can be scaled to high dimensional data. So that's the future work I can think of. And that's the end of my presentation. I'm welcoming any questions. Thank you.
Thank you, Dehao. So now it's time for questions.
So Dehao, I don't think this claim is really tenable that it's independent of the sample distribution. It's independent of an initial sample distribution, but then you use this iterative procedure to sample more, right? So I think that's not correct.
We sample more, but finally we will normalize.
Yeah, but it's, you know, it's of course, I mean, no one can ensure a representation that's independent of the sample distribution, right? You can only, you basically can say it's independent of an initial distribution. but you have to be careful with this claim.
Yeah, I think carefully. Actually, I think very carefully in this claim, and yeah. So, I do some empirical experiment to verify that, but of course it is.
No, but it's just you know it's independent of the initial distribution. But then, of course, you have this iterative procedure to sample the function more, which makes all sense. I'm not saying it doesn't make sense, but you have to be careful with the claim here. And then one other question, one other comment maybe is, it's really very similar. It would be easier to understand your method if you would make it explicit that it is an extension of the old Tony plate method of basically trajectory association with the power vector.
Yeah.
Very similar to this 91 paper of Tony. And it would make it much more easy to understand if you would actually cite that paper.
I see. So my thinking would be, I want to introduce, I want to have my paper self-contained. So
well, it's always good to refer to previous work that is very, very related. You know, it doesn't help to make a paper uncontained by leaving away references that are really relevant here.
Yeah, I can add that reference to my paper.
I hope you did, but also in the talk, it would make it much more easier to understand your method if you would point out that it's how related it is to the trajectory association.
Yeah, sure. Thank you.
I also have a question about this invariant property. So in my understanding, you said this is a distribution invariant because in the end you will get a center of the boundary of the distribution.
Yes.
Right, but in my understanding is the boundary is the boundary of the samples, not the boundary of the where the whole space that the function is defined.
The boundary. The boundary is the boundary of the set of the data distribution, not the boundary of the function. So, for example, your function can be like. So this is your function, and your support of your function maybe look like that. So it may not even be connected. So this may be your support of your function. But after mapping the data to a high dimensional space, it would be like lying on a I think it would lie on a convex domain. So I'm not sure whether it makes sense to you.
Yeah. So because the claim is that the final representation is independent of the which samples you select, but in this respective, I think it's still dependent on which samples are there, which samples you get from the original distribution. Is that correct, or am I missing something?
My claim would be if the data sample is representative enough, then it does not depend. So, for example, as long as suppose this is my support of the function, as long as your data point cover all the samples, it does not matter whether this is denser or sparser. As long as the data covered all the samples, then because if you cover all the samples, if you consider the encoding of X and then the union of all X, so suppose you consider this, it would be a region in a hyperdimensional space. So as long as your data sample is representative enough, then the data would distribute it across the region in a hyperdimensional space. And then if you consider the circle covering all the sample points, then it would converge to the center. I'm not sure it makes sense to you.
Yeah, okay. So yeah, I kind of missed that like jump.
I had a question about the you mentioned inherent data or so by that, are you referring to kind of like whether or not the underlying function is band limited?
So I think it would be better if I explain it with an example. So suppose it is a two-dimensional function, but the support of the function is only a small region like that. Then if in this case, then the dimensional required, so the n required would be only proportional to the size of this region, but not the whole dimensional space. Similarly, if you have a high dimensional, like three-dimensional space, but your support of the function is only lies on a two-dimensional plane, then the required dimension is only two-dimensional. It is proportional to a two-dimensional data. Does it make sense? Yeah.
Yeah, it's kind of like an information theoretic.
Yeah. It's like this is intuitively in this sense.
Okay. And one other quick question, you said PDEs, but the way you sort of formulated it's kind of looked like ODEs. Just want to with those benchmarks.
Yeah. Actually, it's I just used the, because in the previous paper. So here so in the previous paper they all say it is PDE solver. So I just use the terminology they use. So that's just a terminology issue.
Okay. All right. Thank you.
Thank you for your question.
Yeah, I just want to clarify again on this resampling procedure. So does it, to me, it seems that what happens like when you run the algorithm, right, is that effectively independently of the sampling, you force it to be uniform, right? It seems to be like a heuristic to bring the sampling on the function to be uniform. And in that sense, it's independent, but as Fritz was mentioning, I think, so it seemed to be based on the assumption that you secretly assume that it has to be actually uniform, or you have a way to make it to be uniform. Have you been probing that?
Let me think. So it's, yeah, so the intuitive sense is we try to make it uniform, but whether it converges to a uniform sampling, actually we are not very sure. But I think that the major, so suppose so let me give an analogy. Suppose here is a region, and we can, so it's a two-dimensional space. It is a two-dimensional space, and you can have samples drawn from this space. And then if we do such a, if we maximize the minimum distance between x and xi, oh, sorry, minimize the maximum. Suppose we do this optimization method, then the final solution x will converge to the center of the circle, which cover all the points. So that's, so suppose if we solve the optimization problem, then the solution will converge to the center of the circle covering all the points. As long as your point is covering the whole sampling region, then whatever sample distribution or sample density is, the solution will always be the center of the circle covering the whole region. So suppose if you denote all the region as R, then it will be the circle covering the region R. It will be the center of the circle covering the region R. As long as your point is dense enough and cover all the region.
Would it still, I mean, I get this intuition. I'm just trying to understand, like, based on my intuition of using high dimensional computing, because effectively what you're doing, right, you're superimposing lots of key value pairs.
Yeah.
So it's like, it's not like quite the same as if you would find the average point. But maybe it's the best possible. Okay. I mean, I can't, yeah, I'm just trying to say that I'm not sure I fully relate to this explanation, you know, given what is happening in the high dimensional space. But
to my understanding, so that so this finding the center, so this is a kind of second stage. So it's after kind of construction and superposition of key value pairs. So this second, this yes, while loop is kind of refinement. So.
Yeah,
exactly. So technically what is happening, right, in the while loop is that some of the points might be present in the superposition several times, right?
yeah,
this is effectively what's happening, right?
Yes.
So now it's like a weighted superposition of key value pairs, and then it's normalized at the end, right?
Yes.
But maybe finding the center is the best geometric interpretation, and just not able to relate it right now. But yeah, thanks again for providing the explanation.
Yeah, thanks for your question.
So Dehao, one other question. So if you want actually a rectangular kernel for the EX representation, for the FPE, for the domain.
So you mean this one?
Yeah. Why are you using then phase angles that are from a uniform distribution and not phase angles that are drawn in a way that you actually get a rectangular kernel?
Actually, so here in this formula, I'm not desiring rectangular kernel. It is only saying that I hope the distance, I hope the similarity will quickly degenerate to 0, but it maybe.
Yeah, but you could have this exactly. So why do you not use the proper kernel shape? I mean, it's available in the FPE.
Yeah, because suppose we use a rectangular kernel, then it would be discretized. Discretized. If I understand it correctly, it would become a discretized mapping.
What do you mean that? What do you mean by discretized?
So for example, if you have x1 and x1 plus epsilon, then if you map it to the high dimensional space, these two encoding will be totally same as each other. This is what I mean by discretized. I think this rectangular kernel will produce this thing.
Yeah.
Because,
why is that bad if you want this? I mean, you want this, right? So it's
no, we don't want this. We don't want this. Because if you discretize, then there will be information loss when you map the input to a high dimensional space. Actually, we want a smooth kernel, not a rectangular one. Suppose it is a smooth kernel, then it is a continuous.
So why are you then writing it this way? So what do you really want? Why are you not formulating it in a way that you say, you know, that you require a smooth kernel?
Actually, if I need to write it in a rigorous way, I would say it is greater than 1 plus epsilon when the distance is smaller than epsilon naught, and it is smaller than epsilon if this is greater than another epsilon prime. So I think it may be too complicated if you write it in this way. Does it make sense?
So you want the kernel to be 1 plus epsilon?
Oh, sorry, 1 minus. So we want the similarity between, so here.
So do you basically want a triangular kernel? Is this what you want?
Actually not a, so actually whatever kernels does not matter. The only requirement is decays to 0 quickly. As long as it decays to 0 quickly, then it is okay. So like a sync kernel also work, like because it decays to 0 very quickly. And of course,
many kernels decay to 0 very quickly. Right?
Yeah. So we only choose one of them.
Anyway, yeah. So I don't quite understand why you don't write it exactly what you want. So you write it in a way like you want a rectangular kernel, but then you don't want one.
Yeah, maybe this is a little bit confused. So if I write this is equals to 0, then it is a rectangular kernel. But so that's why I write approximately equal. I think that's
okay. Okay.
Yeah, sorry for the confusion, but
No
I may need to think more carefully about. Any other questions?
Hi, thank you for the talk. This is a terminological thing relating to what many of the previous questioners have said. I wonder if rather than calling it distributional invariance, if you called it something like distributional invariance within the support, that
Oh, yeah.
then that might have kept a lot of the previous questioners happy. Then another thing I'm interested in is, and this sort of relates to this distributional invariance and your optimization procedure where you're finding that circle. I wonder if things would become a bit clearer if you were to take your reconstruction error and decompose it into 2 components, or not the reconstruction error, but the actual reconstruction itself, and decompose it into 2 components. We call one the shape, and the other the certainty. And it seems to me that with your resampling procedure that you have there, what you're trying to do is to increase the certainty at various areas within the space. So if basically if you're thinking of your reconstruction at a particular point as being, say, a normal curve, you've got back a particular value which represents the mean, but there's a degree of uncertainty, and in some places where you have very few samples locally, then effectively you've got a very wide spread on your uncertainty. So maybe I wonder if it would be clearer if the claim were that effectively the shape is distributionally invariant within the support, but that the uncertainty is not distributionally invariant within the support. So effectively, by your resampling, you're just trying to increase the certainty in certain areas of the space, even though the shape is known from the beginning. I wonder if that would help with the explanation of what's going on.
So let me rephrase your idea. So basically, if you say there is a function, and then you may have some samples like this, and then you would have uncertainty. For example, if the sample is dense here, then the uncertainty will be small. But if there's a sparse sample, then your uncertainty may be high, like this. So this will be region of uncertainty. And what we want is actually we want to have the certainty to be uniform. Is it what you mean?
Yeah, well, actually, I mean, ideally, you'd like your certainty to be, you'd want not only uniform, but you'd like your certainty to be as your confidence interval, if you're going to use that terminology, to be as narrow as possible. And so, in a sense, your shape, you know from very early on. So you'd be able to argue, even without your resampling procedure, that you're probably on a better ground to argue without the resampling procedure that your shape is relatively distribution invariant within the support, whereas what you're doing with your resampling is you're mostly affecting the local certainty.
I see.
So in a sense, you're taking your claim of distributional invariance and allowing yourself to sort of shovel it around. So you can say this part of what I'm concerned with, I've got more distributional invariance, whereas that part of what I'm concerned with, the certainty part, I've got less distributional invariance. So you're saying, what is it that changes as a function of how I resample?
Sorry, what was your question?
Oh, I guess there wasn't really a question in there. I was just wondering whether that way of thinking about it might be helpful as a way of explaining what's happening in your procedure.
Yeah. I think I haven't thought of like this as a uncertainty. So I think it provides a very good insight. So we can maybe we can model model the distribution as the uncertainty. That's maybe what we can think of.
And given that you've got you talk about reconstruction, I mean, maybe you could use the reconstruction error as a proxy or an actual measurement of that uncertainty. But so your local reconstruction error.
There's a local reconstruction error.
So I mean, so if you were to reinstantiate all your hypervectors repeatedly and look at how the prediction at a particular point changes over the ensemble of different instantiations of the hypervectors,
and see how the reconstruction error.
Well, that would allow you to get some measure of the reconstruction error as a function of that random variation. Yeah, I'm just wondering whether that's a useful conceptual framework for thinking about what's going on there.
Yeah, I think it's
sort of taking a more statistical view.
Yeah, it's a statistical view. Maybe we can have a more precise measure, because here actually we if you do this iterative process very slow, with this process it is actually quite slow, because here if you add the vector one by one, then it can be slow convergence. So I think your trick may be applied when speeding up the convergence of this iterative refinement.
Well, I mean, the other thing there is, I mean, that procedure you have there is, I mean, it means that your mechanism cannot be an online mechanism if you're doing that. Effectively, that's sort of a batch exercise afterwards. And so I think it would be of interest to be able to characterize the performance of what's going on without having to invoke that procedure at all. It just means that if you're doing that, if you're not going to invoke it at all, then you have to learn to live with the uncertainty induced by having sparsely sampled areas of your space, which once again starts to look like a statistical problem. By the way, that this procedure here, is that, I think historically something like that was called something like whitening. If in, say, image processing, where you had a histogram of brightness of pixels or whatever, this seems very similar. You're effectively reweighting different areas of the space to allow you to sort of look uniformly in all areas of your space. So maybe for explanatory purposes, again, it's worth, what are similar procedures that have been carried out elsewhere that capture the same idea but go by a different name in different fields.
Yeah. I think it would be good if I can cite some reference to help explain this iterative refinement.
or it's even looks to me a bit like active learning in a sense, because you know you're exploring your data space in areas where you know that you have low sampling rate.
Yeah, to me it's like a k-mean clustering. Yeah, but never mind. It's quite similar.
Thank you.
Yeah, thank you.
All right, I think we need to wrap up eventually, unless there is a very last minute, last second question. Dehao. Well, if not, first of all, Dehao, thank you very much for your talk. And before you all go, I want to make a couple of other announcements. First of all, about the very last webinar of this season. So this is the open mic webinar, so where we discuss open issues. It will be a hybrid event, so partially physical, so here in Luleå, and also online on 16th. So it won't be on Monday, but on Friday. No, so on Thursday night. So we will discuss open challenges in VSA. And the second announcement is I'm compiling a program for the next season of VSAONLINE. So if you have any cool talks, so please drop me a line. But otherwise, thank you all for attending, and have a great week.
Thank you.
So see you in 2 weeks. Bye.
Good night.
Bye, thanks everyone.
Thank you. Goodbye.